live. We are live, please.
Yes, Navneet.
Navneet, you can play your video.
Yeah, so right, sir.
To be running.
Yeah, we are playing, sir. I'm just playing it.
Yeah.
Navneet sir, the audio is not coming. Can you just stop for a minute?
Just a minute.
On the top, you have 3 dots. You just go to share sound option. On the taskbar, you will have 3 dots.
Yeah, I've done again. Thank you.
Thank you, Navneet. Good evening, friends, and welcome to this very, very interesting show in the era of AI, robotic surgery, where surgeons are going to get extinction dinosaurs. What has been promised. We have a very interesting talk today and some very interesting set of speakers. To top it all with the knowledge of Dr. Virendra Sangwan and Dr. Namrata Sharma to guide us what is happening in real life scenario. In the era of 3D printing, where we are not quite accustomed to it in day-to-day life, few have taken a lead so beautifully to present to the world what can be done with the engineering aspect of ophthalmology and how tissue respect can be done. The talk today is going to be on 3D printing and its applications in ophthalmology. I think it's one of the most fascinating topic that we can talk about and something which can change the whole scenario of corneal donation and eye donations and blindness of 10 million plus people in this country. I guess this could become more and more interesting as the show goes on and we'll have more such shows. In the interest of time, we come up with very, very great speakers today. Each one of them a lot of knowledge to share. We'll have to restrict their time with the promise to get them again and again ever so often because there's a lot to be shared. Our opening batsman is Dr. Vijeta Jaiswal. She's a field application specialist from CellLink Brief Bio. Vijeta is a field application specialist at CellLink. She brings about extensive expertise in 3D bioprinting technologies and provides hands-on technical support across India and the broader APAC region, including Oceania, Southeast Asia, and South Korea. Vijeta is passionate about delivering tailored solutions, strengthening regional collaborations, professionalism, and we would like to hear how we can join hands with the pharma and somebody who could be knowing much more about this with an ophthalmology background. Over to you, Dr. Vijeta. Let's hear what we can do about 3D bioprinting for ocular innovation.
Yes. Thank you so much, Dr. Himanshu. I will share my screen here. Hope you can see my slides.
Yes, yes, Vijeta, we can see.
Yes. So, first of all, thank you so much for having this platform where, all of the knowledge from technology aspect, from medicine aspect, engineering aspect come together, and we can have this beautiful discussion as to how this field is progressing. And thank you for the kind invitation. So, my name is Vijeta, and I'm an application specialist with CellLink. Today, I will be discussing about different 3D bioprinting technologies which enable as well as which helps in the advancement in ocular regeneration. And I'll be discussing about few of the technology in much more detail to tell you how has the advancement occurred in the bioprinting field as well. So the first topic that I would like to talk about is the transition towards 3D modeling system. Uh, as all of us know that conventionally we used to sculpture cells in 2D petri dishes, which was again one of the widely studied area, and most of the tests, most of the studies have been performed in 2D cell culture, but as the system in itself is not physiologically relevant when it comes to translating this to human model. Therefore people started transitioning from two-dimensional cell culture to spheroids, which was again an aggregate of cells in three dimension, but it also somewhere lacked the extracellular matrix representation as well as cell-cell interaction. Therefore came the advent of 3D tissue modeling, wherein you can not only have different types of cells come together, but also cell and ECM interact together in a spatial orientation that you would like to have, and thus create tissue structures which can now be put forward for any kind of studies, for any kind of testing. And that's where 3D printing, 3D bioprinting comes into usage. So, to introduce the topic to you, 3D bioprinting, again, it is a derivative of a bigger terminology known as additive manufacturing, where you take a material and you put it across in a layer by layer fashion, giving rise to the 3D model. So, in 3D printing, you actually work with materials like ceramic, plastic, metals, whereas in bioprinting, we usually work with biomaterials, which can be a range of extracellular matrices. And along with cells, we put it together in a spatial orientation that we would like to achieve, and thus use these models for our downstream applications. The workflow that one follows in 3D printing, 3D bioprinting would be such and such, where first we need to look at what kind of 3D model we want to print, and we need to design that 3D model. For example, if somebody wants to print a corneal lenticule, then designing the exact size, the depth, and the shape of the lenticule is very important. And this is one of the important aspects in the bioprinting workflow. And second would be deciding what material to print it with, what kind of cells to print it with. So preparation of their biomaterial ink, which would finally create their 3D model. Now, in this bioprinting area, again, there are different technologies which enable you to print your model, and identifying the right technology that will suit your biomaterial ink as well as the model also is an important aspect. Later comes a step of cross-linking, which is again very much material dependent, wherein you cross-link the polymer that you are working with and culture it and further take it down for downstream analysis. So this workflow remains common and it sort of gets integrated in the current 2D cell culture work. Now, 3D bioprinting is such an area which has not only, not only expanding in the simple modeling area, like you can create disease models, drug testing models, as well as drug discovery model. But now the kind of technology that we have, it also enables us to create vasculature in our systems. It enables us to create organ on a chip platforms. It enables us to create even constructs which like cornea or heart valves, complex structures printed with extracellular matrices, collagen. So we are approaching and we are nearing to creating much more human relevant systems, thus trying to bridge the gap between two-dimensional system and animal models, and also trying to reduce the number of animal tests that we do. So to move ahead and talk a bit about the technology which helps us do all of this. So broadly, we categorize the bioprinting technologies into these three areas. The first one, known as extrusion-based bioprinting. I'm sure many of the speakers here would also talk about this technology being used in their research area. So in extrusion-based bioprinting, we use external pressure to push our material out of a nozzle, and the material goes around in the dimension, in the shape that the model instructs it to, thus creating the 3D architecture, the 3D tissue model. Then there is another technology known as inkjet-based printing, where rather than having filament of material, you have continuous droplet being deposited and give rise to your 3D tissue model. Lastly, we have light-based bioprinting, where we use visible light source to create our 3D model along with photopolymerizable polymers. So in my presentation today, I will be discussing more on the light-based technology, light-based bioprinting technology, which helps in much more advanced biomaterial printing, as well as fabricating, constructs in with the help of visible light in a much more easier fashion. So introducing you one of the printers that we have, known as BioNova X. It is a DLP-based bioprinter designed for high resolution, high speed, and in-well multicellular multi-stiffness printing. So let us have a look at how this technology works. So as I mentioned, that digital light projection-based printing, it uses visible light source to, so the visible light source is projected via an industrial projector, and the projector projects different 2D layers of your 3D model. So you take your 3D model, slice it into different 2D layers, and each of the layer is projected as a light image which falls onto your photocurable biopolymer. So as you shine light layer by layer, the biomaterial ink which is present in your well plate gets cross-linked. So to highlight this mechanism, I have this video here which shows how real-time printing with BioNova X happens. So you have your biomaterial ink in a well plate, and the light is guided via printing probes inside the well plate, therefore creating your constructs directly inside well. Again, the ink here can be laden with cells because we print with 405 nanometer of printing technology. Therefore, you can also print live cell with these kind of printers. And once you have your fabricated material, again, it can be of different size, shape, and it can constitute of different types of cells as well as material. You can use them for your downstream application. So BioNova X is one of our high-end DLP printers. As I said, it is designed for high resolution printing. So you can achieve somewhere close to 10 micron print resolution with this kind of printer. And the printing is more of like smooth and layerless. So once you observe the printed constructs, there are like no staircase effect or no layer effect that you can actually visualize, thus helping you create constructs of high resolution. So let's say if somebody is again looking to create corneal lenticules or lenses, then this would be the ideal technology to go for. And another thing that this kind of technology is enabled with is, since you print with light source, so you can also tune the light source and vary the stiffness across your printed constructs, thus helping you create a multi-stiffness 3D model. So again, somebody who is looking to work in the area of ocular regeneration, or maybe study a disease model, this multi-stiffness feature comes into much more use, because you can, from one single matrix itself, you can have variation in stiffnesses, and you can have different cells placed in different stiffness, does help you maybe study some kind of stromal invasion pattern, or maybe help you achieve a completely different construct by something known as 4D printing, where this kind of regional stiffnesses can help you create a 4D architecture from a 3D printed model. Along with this, the printer is also equipped with something known as multi-material printing or multicellular printing, where not only one but 6 different types of materials can be printed across XY as well as across Z, thus giving you the ability to have different types of cells placed in different layers or in different locations in the XY horizon, and give you a multicellular aspect of a complete model together. So this kind of printing technology, again, it is completely achievable with our extrusion-based system as well as the DLP. But the DLP printers help you, achieve this kind, mainly the ocular models in a much more easier fashion. So with this, again, our company, we deal with the entire workflow of bioprinting, and we have different kind of ECM-based, different kind of biomaterial based bio ink which are developed for different tissue types in the body, and also we have specialized one for retinal cells, retinal organoids. um, so with this I would like to end my talk here, and again, all of these technologies can be accessed at our COE facility, which is based in IISc. It's in the Department of Bioengineering, where we are housing all these printers. And anybody who is interested to work with these technologies or do some proof of concept, we'll be very happy to have them at the facility. Yeah. And with this, I'll be happy to take any questions that you have for the technology.
Yes.
Sir.
Thanks, Dr. Vijeta. It was brilliant. I think totally different perspective about it. What is it that we are lacking from day-to-day clinical? How far are we away from the real application that we are today?
Yes, yes. So the thing is that all of the research that has happened so far, I mean, I think we have progressed toward the, there are some players who have already progressed toward the clinical stage. It's basically trying to test their own material in patients and see whether that works or not, right? So I think that this is the right time to say that yes, we are more or less towards the clinical trial phase, and it won't be far that these technologies would actually be used in patients maybe in a year or in a year and a half from now on. Yeah.
So that's some timeline, that year or so that you're talking about, that we
Yes.
could be seeing real time with the
Yes.
mRNA vaccine, mRNA, the vaccines which have come up. Does that
Yes.
help you to develop these kind of stuff now with the cancer specific stuff and all? Does it help you? So, Dr.
Uh,
Sangwan, would you like to ask any questions?
No, Dr. Himanshu, I think it's absolutely fine, and it's a very good, start with Vijeta's talk. And maybe, now the natural might be Vineet, talk. They actually use this printer in LVP for corneal application. So maybe if everyone is okay, we can have his talk next, so that
John,
there,
you're next.
John, if that's okay with you.
Yes.
Yes, sir. Yes, sir. Sure.
But to me, sir, I've been following and doing this from 2013, 3D printing of different things. Now the field is pretty advanced, and we are very close to human clinical application. John will talk about other kind of devices that we can use printing. We started in LVP 3D printing for engineering the eye program with the this IIT Hyderabad and MIT Boston. So there is quite a bit of progress, and today's talk is basically will give this flavor from different part of the country that what is being done. Thank you.
I think amazing. That's a lot of things have been said and done about the whole thing. We have another great speaker, Dr. John. John needs no introduction, actually.
I think we are going for Dr. Vineet. Is that
हिमांशु
possible?
विनीत जोशी के लिए करते हैं, क्योंकि वो और इनकी विजेता की टॉक वेरी सिमिलर हैं, बिकॉज दे यूज दिस प्रिंटर व्हाट विजेता टॉक्ड अबाउट.
Vineet, would you like to come back
कैन यू
on?
स्पीक विनीत?
Yes. Am I audible?
Yes,
Yeah.
absolutely, Vineet. Pleasure to have you there, and thanks for your time. No better person than you to talk about how to take this further in day-to-day activities.
Just let me know if you are able to see my
Yeah, we can
Yes.
see the slides.
Yes.
Yeah, not full
Okay.
screen yet, but we can see the screen.
Okay. Thank you. Thank you,
Yes.
sir, for this opportunity. Thank you, AIOS, Namrata ma'am, Virender sir, and Micro Labs for giving me this chance. So I will finish the story which Vijeta started. And we actually visited their site last year, trying to explore some new technologies where how we can really bring bioprinting, like print corneal tissue with cells. And you have to think both ways, as John was saying earlier, as an engineer and as well as a clinician. And how we can do this, I think Vijeta has really simplified my job. So I will directly dive into what looks like a possible way towards printing corneas for clinics for transplants. Okay, so we all know this, that in India and in African subcontinent and many other countries, corneal blindness is the most second most common cause of preventable blindness, and we have very steep targets coming up. Every year the backlog increases. The iBank network, although being very good, and we are working hard in it, but there needs to be some alternative, because we have a larger target to meet. And maybe someday, if we meet our targets, we will be able to help other countries who are basically in dire need of this particular preventable part of blindness. Okay, so I'll quickly jump to what corneal regeneration will look like, and I'll just focus on the last two parts, which is basically if you have a corneal scar which is deeper or full thickness, which means that you would have to replace it with either a full thickness or a lamellar corneal transplant. And in those contexts, you would have to replace it with something which has a structure, a curvature, and transparency like cornea. And how can you do that? So Vijita just showed us a way that there are ways by which you can actually fabricate a tissue. But if you talk in perspective of cornea, you can simplify it for clinicians, that you can maybe make a full thickness corneal construct. Maybe you can also print anterior lamellar or posterior lamellar construct. And as a clinician, when you're talking about printing corneal tissue, I'm talking about, in same language, printing it with cells and extracellular matrix. Now, it might not be possible for us to get the entire extracellular matrix as sourced from human corneas. Yes, we have tried that, but again, we are limiting ourselves to the need of cadaveric tissues. So there is a way we can maybe replace it with some acceptable bioinks or biomaterials. And when we introduce such foreign materials, we have to, as a clinicians, study in depth, and as clinician scientists study how the epithelium would interact with these materials, how the stromal components like the native keratocytes would react with these materials, and how would these materials swell, deswell, how will they react with endothelium, basically to maintain the transparency. Or will the biomaterial itself have superior properties than an extracellular matrix of cornea? So these are the studies which you will have to break down corneal bioprinting into. If you are precise enough in your printing strategies, one day you might be also able to print specific anterior lamellar construct and posterior lamellar constructs, wherein probably you would use them as DALK or ALK constructs, or you can just put it as intrastromal inlays, like for in keratoconus nowadays. We are looking forward to that kind of therapy to treat steep corneas. Here again, you have to look into the interaction of epithelium, blood vessels, immune reaction that is happening, and also look at constructs that you can print which can promote corneal nerve ingrowth and also be inert at the same time. So there are a lot of things. So this is something that is very complex, where you have to look at the composition of the ink, the composition of the cells, and then figure out a designing strategy, and then select a proper tool, as Vijeta was showing, either an extrusion printing or a light-based printing. Okay, so the whole race towards bioprinting and why it is gaining a lot of attraction now is because of this. So previously, it was possible to seed cells on the top of a 3D culture. Okay, but to get the cells at all the constant or at all the depths in equal concentration was very difficult. It depended on the properties of the cells to grow in. And that's where 3D printing becomes so beautiful, because you can now lay down layer by layer, z-axis layers on, stack them up, which are loaded with cells. So that gives you a more better opportunity to construct a biologically functional tissue. And that exactly is 3D bioprinting. So Vijeta has covered this part, but there are a lot of things that you have to control while you're printing a construct, which means the viscosity. It's just like you have to make a ink which has cells and extracellular matrix. Now you can replace this extracellular matrix with other inks, which I will just show you in the next slide. But their overall consistency is what will determine how you are able to print. They are very much like viscoelastics, how we use in cataract surgery. And we have to control how they gillate based on the temperature gradients, based on their pH gradients, what are their contents, and that is how you will build the bio ink. So bio ink means you're going to use that as a substitute of corneal stroma, which is gel-like, which will flow through the nozzle of the printer, and you will be able to carve it in the shape that you have given in the CAD model. So there are many alternatives, which there are various groups across the world who have tried printing with hyaluronic acid, alginate, gelatin, chitosan, even silk fibroin. What we tried here was, I was mentioning earlier, is deriving an extracellular matrix specialized ink from human cadaveric corneas and bovine cadaveric corneas, and use that as an ink for a bioprinting. So a lot of these strategies are needed. And once you finalize your ink, then you have to finalize your cross-linking strategies. This is very similar to what we do in keratoconus. It's basically hardening the printed construct so that it retains its shape which you have given it to. Otherwise, it will print in a round shape and then flow away. We don't want it to flow away. We want it to retain that particular shape. So there are a lot of groups who have tried this, and they've used both extrusion as well as light-based bioprinting, and they have come up with different strategies to put these things together. Okay, so I'll just show you how to do it with how we have been trying to do it with extrusion printing and light-based printing. So typically in extrusion printing, what we will do is we will load this gel-like ink in the printer nozzle, and then it do test runs as to what pressure and what a property of cross-linking that we are going to use. So the light source, specific light source like 370 nanometer or 404 nanometer or 570 nanometer, there are different light sources in these printers, and then we can use them, and a photo cross linker, just like riboflavin, there are many other photo cross linkers to cross link the gel in that curved shape. Now how to get that curved shape? First you have to build this mold, and this is where something like FDM printing, which John will be talking about, comes into real handiwork. So we have used a stereolithography printer here, but this curvature is derived from a patient's topography. And here you can do both ways. You can print it convex or you can print it concave. What you're seeing here is a block of a contact lens construct used to print a scleral contact lens, and we use that to print a gel into it. But this is how exactly the extrusion printer prints if you want to get a curved construct. It's not easy, I would say. You have to really make a 3D model. The extrusion printers are actually built to print on a flat sheet. So if you want to print it on a curved surface, you have to design a new code by which it is able to go spiral and give you a particular kind of a shape that you want. So what you're seeing are the extrusion printed construct from a printer which Vijeta was showing. We have got this same printer from their group, and this is how you will be able to print. So the problems with extrusion printing are that the nozzle size, you cannot go below 150 micron, because if you go below that, you will not be able to print with cells. The cells will die because of the pressure through which you are extruding them out. So again, if you are limited to 150 microns, then you can't print a very high resolution construct, because corneal thickness is up to 600 microns. So what basically you will see a structure like this, okay, so which is curved, but it is not precise. It's not accurate. You're not getting that finesse that you want in there. You can also try printing flat sheets and then maybe punch out a cornea out of it. We've tried that, it works, but again, the edge, if it is satisfactory for a full thickness construct, but it doesn't work fully. So what the material, again, what we have used here is a bovine corneal extracellular matrix, which is decellularized, and then we use a cross-linking agent of a white light. So these are the for like the drawbacks of using extrusion printing. One being the handling. So many times it is very cheesy. You can't hold it properly. It cuts through the sutures when you try to suture them. If you cross link it too much, it will become like a hard button. So you will have to then, you won't be able to hold it properly. You will have to use a forceps and guide it in. So the depth of resolution microarchitecture, what you would want in a proper corneal construct, might not be there. And there are variations in cross-linking, like the upper surface might get more cross-link, the lower might not, which affects the biomechanical strength and the overall suturability. It's a very good approach, but you need something more precise. As you know, the corneal structure is extremely delicate, and the fiber spacing is so intricate at like literally 65 micron spacing between every fibril, and these lamellae are stacked over each other so beautifully and orthogonally in the center, which is responsible for its transparency. Now we cannot reach till nanometer level, but can we reach till the least micron level so that we can build a good scaffold which the keratocytes might feel friendly? And that's where the Bionova printer is something what we tried. We have gotten this from Vijita's team. And so what we do is we make these specialized CAD models and we load it in this printer. And we have really made a protocol by which you can print a cornea out of this. It's quite complex because you have to make sure this one prints in a well plate. So you have to adjust a lot of dimensions, and the bio ink formulation here has to be sensitive to the 404 nanometer light, where it will cross link the shape that you want. Now this printer is very accurate, especially it gives very high resolution prints up to 20-30 microns, and you can see the quality of print is good, it's precise, it's fine. It even feels like a cornea when you hold it, and it's quite transparent. Here we have used a gelatin based ink, and we have used a different type of a photo cross linker. We call it LAP. It is like riboflavin, and you can actually hold it with a forceps. So this is how it looks like, but you can really do wonders with this as a surgeon. Now what I'm showing you here is we could print constructs 10 millimeter large, we could print them 8 millimeter large, and they were of the exact size which we measured using the AIOSSC. So what you are seeing is a 8 millimeter cap, which is so pre-cut desec lenticule. We removed the cap and we printed the exact dimension and placed on top of it, and you can see that it is snugly fitting. So that is the amount of accuracy you get. We were also able to print smaller 5 inlays. So for example, if you want to do a keratoconus surgery, so you can actually print a smaller lenticule, 5.5 in diameter. And actually what I did, this is all wet lab practice with cadaveric corneas. You can place a sheets glide and actually put this thin lenticule inside. And what you're seeing is real time, is where actually we actually printed it quite steep, and then I realized that it is tenting the cornea too much, and I asked my engineers to change the CAD model and print it. In half an hour I was able to print a customized construct as per my need, and then put it again inside and measure topography of it. So that is the customization 3D printing will give you in future, where you can make the constructs as per your need, as per the patient's need. This is something new, fresh from the lab. We also tried printing Cares lenticules loaded with stem cells. We tried putting it. I'll be coming up with a video of it very soon, and it works very good. I mean, the concept is same. If you have the correct CAD model design, you will be able to replicate it with extracellular matrix and cells and use it as per the surgeon's need. And that customization from surgeon's point of view is what 3D printing makes very interesting. Can you customize it for the patient? Yes, you can. So we are working on this mega project where we are trying to take data from the patients based on their scar. We like their topography, their ASOCT parameters, their densitometry parameters. And we are trying to develop a software which can map this, and we'll be able to generate a therapeutic guideline for a patient and then translate it into bioprinting. So you can really customize the therapy up till the patient's level. So recently we got a grant from BFI Biome organization, a summer grant with IISc Bangalore, where we will try to now take this one step forward and print these customized constructs and even try to load them with drugs, for example, antiviral or antifungal drugs. And this is just started. So the logic remains the same. Because the DLP printer ink is liquid, you have a chance to actually seed it with cells and drugs. We don't know how it will go, but this is something new which we have started. And the power of this printer is that you can't reach the nanostructure, but can you reach the microstructure? And that is what we've tried to do. We're trying to make a mesh-like, grid-like pattern where we can actually develop a more biomechanically strong construct for diseases like keratoconus. And that's how it looks like as of now. So we are still testing this out, but it's quite amazing to see how accurate this printer does the job. We've also tried different biomaterials like silk derived from natural. This is another natural biomaterial like collagen, and silk-based hydrogels are quite popular in different areas of biomaterials. Like they've been using it for liver and many other organ regeneration. We tried it for cornea. So far looks good, but what was a surprise finding was its adhesive property. So we are trying to look more into it and see if we will be able to use them. And we found that it is very nicely compatible with epithelial as well as stromal cells. Sometimes you might not even need bioprinting. You might just get away with a good gel. And I think this is an inspiration from Dr. Sangwan, where you can just apply the gel and then place a contact lens over it, and probably you might get away by dealing with smaller scars. So yes, so summary, this is a team effort. I've been very lucky from LPI to get this opportunity. We are trying to develop these new solutions which can customize for the surgeons and the patients, and hopefully we'll be able to contribute to corneal blindness and help our patients in our country and others. This is all thanks to my team, my mentors, who have really supported me so far, and we're going with whatever we have got now, and we have collaborated with IIT Hyderabad, IISc Bangalore, and hopefully we'll be able to contribute something. Thank you.
Thank you very much, Dr. Vineet. A wonderful presentation. Just a corollary, any other human organ has had a 3D printing in real life scenario?
Yes.
Yes.
There are many. I mean, the trachea has been printed and used in Sweden.
They're very close with skin and bones right now. They're very close. So even liver ductules, biliary ductules is something they're working in IISc. They're very close.
I think, sir, the transparent organ such as a cornea is one of the more difficult things to 3D print. Opaque objects, other more forgiving organs are easier to 3D print.
Yeah, of course.
Yes. The challenge in cornea is the shape and transparency both, because that is what is guiding the vision. And others like liver or even trachea, as like sir said, shape doesn't matter much. It's more about biointegration and function. So it's a different challenge.
Chalo, wait till Professor Mani Luthra's talk. We may not be needing all these things. So you'll be surprised to see something very different.
At this point, I would like to welcome Dr. Pandian from AIIMS. Sir, would you like to have some comments from you on this?
I think it's amazing the way how the technology, especially DLP, we always wanted about photolithography. Now that's coming out as a good technology for doing this. I'm really very happy to see the developments, especially Vineet's work. I'm very happy about it to see. We used to call it as photolithography. Now the transformation is amazing in case of technology wise. Great.
Any animal studies have been done, Vineet? Not yet.
We are currently undergoing one study. So the animal study is mainly to check if our material combinations are working fine. What I showed you was mainly the designing component, which could be universal. Like you can have your own ink developed in your institute, and the way you design it and deliver it to the patient would be something that my focus was so far.
I think the most important thing is how the the physiology, human physiology, responds to it. I mean, because there's always a human response, and I think we need that integration of the, how it is going to get integrated ultimately into live tissues. That is the most important thing.
So we
That
have
way,
done
that way, like you said, I find Dr. Sangwan's solution very simple, where gel is used and it clears the opacity. But then, of course, this is a different, different
Yeah,
trajectory.
that may not clear all kinds of scars,
All kinds
and
of,
deeper scars.
we
The one
have
which we are
done
trying to
hydrogel.
develop here is that we have slightly a different type of model we are trying to use it. I mean, as of now, I'm unable to explain completely, but the one which we have another small tweak in the whole technology. I mean, it's not classically, it's an extrusion technique, but we have something very special. So I think soon, we'll be able to put out something about it. We have been developing it, but still we unable to reach the ink which is specific for the technology what we are using. We got stuck in that. Probably we'll also get one more a slightly modified technique to make it to go less than 150 micron. So I mean, reaching 150 micron is something which is very interesting. But I ask the cells, considering the cell size, we have a limitation about it. But I think that when we go in this current technique, what we are trying to do is slightly tweaked, so we'll be able to get much more, the tensile strength of the printed one and optical clarity we might get much better. Let us see. It's very interesting to see photolithography mediated corneas. I'm very happy to see the results.
So what Dr. Velpandian showed me was really transparent and also biomechanically appeared very stable. But I think everybody is working on these kind of models.
Different it is. Very
Wonderful. I
interesting.
mean,
This
this is excellent, phenomenal thing that is for a common person to understand. But from a personal perspective and how, with minus an institution, what can be done. We have our next speaker, Dr. John Davis, a wonderful human being, glaucoma, cataract, and refractive surgeon. He doesn't need much introduction, but just for the beginners' for sake, he has innovated the foldable fundoscope, virtual reality perimeter, the smartphone ophthalmic imaging, augmented reality, artificial intelligence, Raspberry Pi based surgical recorder, 3D printed. Now, if I keep going on, he'll have no time to speak. So I shall stop here. He has too many accolades. He's really an innovative guy and an engineer at the right place at the right time in the field of ophthalmology with the AI and things going. He's going to talk to us on my 3D printed innovations, how you can get started. Now, this for a common man like me is where I want to start with. How can I be initiated into this?
Thank
Over
you
to
so much. Thank you so much for the kind introduction, sir. And I call myself an eye engineer because I would have become an engineer, but then I finally became an engineer of the eye. Is my screen visible?
Yes, slides are on.
Okay, sure. I'll get on with it. So 3D printing in ophthalmology, as we have seen, we saw a lot of bioprinting, but I am not into bioprinting. I am more into making gadgets and all adapters and things like that, surgical instruments and all that. And some of these models, I have uploaded them free of charge on these websites. This is the National Institute of Health 3D Exchange website and the Thingiverse website, where you can download these models for free and 3D print them yourself. So you can download, get to a 3D printing shop and 3D print them for yourself. So we saw the process of 3D printing. It starts with designing a CAD model, and then you do a slicing with the appropriate slicer software for that particular type of printer. And then you use the printer to 3D print or physically make the product. And then you might have to do some post processing. You might have to smoothen the edges. You might have to put it in the UV light and all those things. And then you get the finished product. So this is 3D printing in general. And these are the materials used in 3D printing in general. So polylactic acid is one of the cheapest and the most commonly used, most easily printable one. ABS is a type of plastic which is much stronger and heat resistant. And then you can get nylon, PETG, and all these things. You get materials which are flexible, materials which are heat resistant, carbon fiber infused, wood infused, and then you have metals, titanium, stainless steel, which require different types of 3D printers. So the most commonly accessible ones are the FDM, the fused deposition modeling printers. So that is what it's an extrusion type of printer, as Dr. Vineet was telling, and these can be used at home. There are no chemical fumes or anything. And then if you look at the other things, there's the inkjet, there's a resin printer, and then you get to the high resolution laser sintering printers. These can print in metal, titanium and other metals and so on. So these are all the materials which are available and can be used. I'm not going into more detail in that. But for us in ophthalmology, everything from the cornea, that is where we started just now, up to the lens, retina, can these be printed? Let's find out. So first, I will just go to my 3D printed innovations. So what I did was I did small 3D printed projects here and there, and got postgraduate students and MBBS students interested in these things, and so they started doing their own projects with me. So these are some of the projects that I have done. So if you look at this article, this shows all the 3D, some of the 3D printing ophthalmic products available, and the different areas in which 3D printing is being used in ophthalmology. I first, let me tell you about the eye drop guide. This I did with a postgraduate student who is just passed out now. So the eye drop guide, it's a device to help the eye drop bottle sit in place so that the eye drop can fall directly into the eye. So this was a problem statement that we put together, and my postgraduate student, Dr. Ankit, he was able to think that we should get a shape like this and get it into. This is a video that we presented about that. Let me go to the next 3D printed innovation which we did. So this is a punctal plug which I did with the help of two very enthusiastic MBBS third year students, ophthalmology students. So I was taking class for them. I taught them about many things, including 3D printing. And then they said, okay, let's do something. And this is a project which we did. So if you look at this on the right side here, this is a resin printed punctal plug. So resin printing allows much higher resolution than FDM printing. So this is on the tip of a 26 gauge needle, a punctal plug is being held. So this was done using resin 3D printing. The modeling was done by the MBBS students themselves under my guidance, and they have also shared it online. This is where you can download it. Mind you, that was just a proof of concept. We didn't use it in patients directly because of biocompatibility and other issues. And this is another project which I did myself. This is a 3D printed glaucoma drainage device. So this was because the need was I wanted to start doing glaucoma drainage device implantation, and I needed to practice in the wet lab. So I just designed a 3D model myself using FreeCAD, 3D printed it using resin, and used it in the wet lab. The video is here for those who are interested. You can just scan this QR code, and the designs are here in this other QR code. You can download, 3D print them yourself, and use it in the wet lab. And then there are MIGS. So I wanted to start minimally invasive glaucoma surgeries. So I just drew the 3D model of the Kahoot dual blade, of the eye stent and whatnot, and 3D printed them so that I can have them in the OPD to show the patients and to teach the students and all that. So this is where you can get the 3D, the video of that, and the 3D models are also available on the NIH website. And you can also use virtual reality, augmented reality, in fact, here. Augmented reality should display the 3D models to patients and students. So that is a augmented reality of the 3D model. Then there are other surgical instruments. So, the irrigation aspiration cannula, the phaco probe, the different types of choppers and dialers, the BHEX, the 3D printed IOL, all these designs, you can iterate on these designs, and you can make new innovations, you can make new designs, test them out before you finalize a design. So that is one use of 3D printing. Then here is a cataract surgery large size model. So this was to teach students how to do cataract surgery, the phaco techniques. It's very difficult to show them on a very small eye even in the wet lab. So we 3D printed this, where the blue shows the stained anterior capsule, the yellow is a nucleus, which is pre-cut for different types of phaco divide and conquer and chop and all that. And this is very large size, so then you can show exactly what you mean by hold the piece with the phaco probe, move it up a little bit, chop down and out. All those things make sense when it is in a large scale. So this is this is with Dr. Rohit Rao. I designed the 3D models. He was instrumental in printing it and making the video. Then, of course, the foldable fundoscope. This was made during COVID times. I had an idea in mind to have a foldable fundus camera which you can put in your pocket. So I sat and learned 3D modeling from YouTube and designed this. And that is how I got to design and 3D print the foldable fundoscope. So this is model number 1. After many iterations, this is one of the later models. And this is currently patented. So that was also the device which won third prize in our LBPI hackathon and got into incubation. So that is 3D printed foldable fundoscope. So how did I design it? I learned 3D designing, made CAD drawings, used 3D printing, and you can do all these too. You can sit and learn 3D designing and do all that, or you can download the 3D models which are already available and get started with 3D printing and then decide what to do later. So I'll skip ahead to how you can get started. So to get started, you might want to get a 3D printer, and 3D printers are not very expensive. So you can get some basic 3D printers for 15,000 to 20,000 rupees. These are all FDM printers. Resin SLA printers are also not very expensive. You can get them for 20,000, 25,000 rupees. And the material used is the FDM printers material is probably around 800 rupees for a kilogram worth. Then to start designing, instead of learning 3D designing completely, you can go to Tinkercad. You go to Tinkercad, you can start designing by just putting shapes together. So this is how Tinkercad designing looks. So you can just start by using all these shapes, put them together, and then you can cut out shapes from them, and you can use your freehand drawing tool to draw that. And once you have that, you just export them, click export, export them to an STL file. And this is the 3D printing process. Once you export them into an STL file, you put them into a slicer software. So if you would typically use something like Ultimaker Cura, put the design there and then slice it so that you can convert it into the code for the particular 3D printer, and then you can print it. But now with the help of newer AI, you can just use a photograph, upload the photograph and tell the AI that I want a 3D model of this. The AI will do the designing for you. You don't have to go to YouTube and start learning 3D designing. So AI, this is meshy.ai, very useful to get 3D models done from pictures or even from text. You can just type in what you want. And this is hyper3d.ai. This can also be used. So you can take multiple pictures of an object and put those pictures together. So that is basically photogrammetry, and get the 3D model as an output from this software. And then you can use these to get to a 3D printer shop. You don't have to buy the 3D printer. Go to a 3D printer shop near you. Tell them that, okay, I want to get 5 prints of this. They'll print it for you. Mind you, the 3D prints might take several hours, but you can get it done. So I'm going to stop right here because I think I've exceeded my time a little bit. Hope that was very useful and inspires you to start 3D designing, 3D printing.
Amazing, amazing, John. As always, clean, bold. Hats off, phenomenal innovation at every point of time. And with the AI, as you've given some good sites, we can put in the designs and it'll make it for me. I really don't have to have no CAD CAM. I don't need to learn any software. Dr. Pandyan is nodding his head. So would you like to say something?
Yeah. I think I could see myself in him. Initially we thought we all of us gone with the FreeCAD. So amazing software that, that bit along with the developments, we could do a lot of things in the possibilities. I could see all, the way what we have gone through. We could understand, the way how we get excited while we work upon 3D printing and FDM. Excellent. I appreciate you for this.
Thank you, sir. I was on the I had to choose between FreeCAD and Fusion 360, and then I sought open source, not under a company.
Exactly, all of us, very comfortable and very nice.
And thanks for sharing with all the QR codes that you're giving. You're making life so much more easier. I'm stupid if I don't do this. You're giving all, I mean, absolute spoon feeding like a school kid. Dr. Mani, are you there? You'll be next if you're there. Yes, yes. So, Dr. Salman, would you like to comment anywhere here?
No, I think it's fantastic. John has given us a very good menu of what he already has created, and I'm going to connect with him offline and get some of these things for our innovation lab at Sarof.
Yes, sir.
Now we'll listen to Dr. Professor Mani Luthra.
Yes, Dr. Mani is.
Can you see my slides?
Yes, ma'am. So Dr. Mani is off to Manali tomorrow.
Oh.
So before she leaves for Manali, we would like to hear about the self-assembly of collagen into cornea-like material inside a corneoscleral rim. Over to you, Dr. Mani. Very interesting.
I'm extremely grateful to AIOS and Dr. Namrata and Dr. Sangwan for giving me this opportunity to speak to all of you. Although I really feel like an anomaly here among these high-tech talks. And so I'm going to talk about something extremely, extremely simple. And this is how this is a journey about how we actually try to make a cornea-like material or cornea-like tissue using discarded corneoscleral rims. So what I'll not bother you with.
So can we just have it on the slideshow, Dr. Mani?
Is this fine?
Yes,
You
that
click
one.
on this. Yeah, now perfect.
Yes, ma'am.
Okay, so basically, what we did was to look at the corneoscleral rim, and that, of course, you all are very familiar with. So this is an actual corneoscleral rim from which the donor cornea has been removed for keratoplasty. And in panel A, I've shown you the rim with the epithelial surface facing upwards, while in B, it's the same rim with the epithelial surface facing downwards. So this is the material that has been used to generate the cornea-like stuff. So, and this is the workflow that has been followed. So very briefly, I'll tell you the workflow so that you get the gist of it. So we use this corneoscleral rim and we put it epithelial side down in a 6-well plate and then poured collagen into it. So I'll go to the details later, but this is just a brief about the overview of the thing. And so we used collagen type 1 because that's the most major part which forms the stroma of the cornea. And we naturally cross-linked it, just like you do in the clinics with riboflavin and UVA. And after doing this, we left it overnight. And in the morning, when we pull off the rim, because the collagen has polymerized, it has polymerized not only within this rim, where the central cavity was there, which was initially occupied by the cornea, but it polymerizes outside of the rim also, like above and below it. So when you pull it off using a forceps, what we saw was that the circular cavity, which was occupied by the cornea earlier, is now occupied by the collagen-like material, which we call CLM. And this actually turned out to be with the same refractive index, curvature, transparency as that of a natural cornea. Now we wanted to examine whether this is biocompatible or not. So for that, we turned it upside down. So basically, we allowed this part to be reversed now, as I showed you in the previous slide, and with the epithelial surface up, so that we could use that to add human corneal limbal epithelial cells on the surface of the CLM. And we allowed them to grow, and I'll go to the details of it. And then we terminated the experiment at day 12, so starting from day 1 to day 12. And at the termination, we removed this cornea-like tissue. So when we have cellularized the cornea-like material, we call it the cornea-like tissue, or CLT. And we determined all its properties to characterize it, to see whether we have native-like cornea in our hands or not. So this is the timeline for the generation of the cornea-like tissue. Day 0, we have used the collagen solution, 1.5 mg per ml, on the epithelial side facing downward. So that's like a cup that we use the scaffold, that is the corneoscleral rim, and allow the collagen to polymerize in it. What you would expect is that the cup would be filled with polymerized collagen, like a gel, but that's where the beauty of the material is. That is, the corneoscleral rim itself, the rim is having some kind of a property. We believe it's like a morphogenetic influence of the rim in the knife tissue, which allows it to behave differently, allows the collagen to behave differently inside the cavity of the rim, and the collagen which is there above and below and on the sides of that rim in the 6-well plate. So with that, when you pick up the corneal rim from the gelled collagen, you see that the rest of the collagen solution actually just slows off, and what is occupied in the central cavity is the material which is just like a native cornea. And you add these cells to it, and we check the biocompatibility by adding the HCLE cells, allowing them to proliferate and grow them in the differentiation media, and then finally stratify them over 6 days, so that at the end of the experiment, we were able to characterize it. So going to the characterization, so this is the how the material looks like when you pull off the collagen polymerized corneoscleral rim out of the plate after an overnight incubation. And this is what happens. That is, we believe that there's a differential polymerization of collagen, which is resulting in a phase separation of collagen into a collagen poor solution, which is above and below this material, and into a collagen rich solution, which is actually the one which is in the middle of the corneoscleral rim, which is in the region which was occupied by the cornea earlier. So that this is what you result in, and it results in the collagen being very well integrated with the outer boundaries of the rim, and it gives you a transmission which is like around more than 70% after at wavelength of 450 nanometer and above, so that it is about 72 to 82 percentage from 450 to 600 nanometers, and above 600 to 800 nanometers, it is approaching 90%. So this is the kind of transmittance that you see. In order to be able to see whether cells are infiltrating into the CLM from the rim, we looked at the keratocytes which have come into the rim from, and they start populating the collagen-like material from day 3 onwards. And you could have all kinds of cells coming in, but that's the keratocytes that we have looked for, because when we stained it with keratocan, we were able to see these keratocytes. And so it was evident that this CLM is able to allow the cells to be infiltrated as well as grow in the material. Now, when we did this experiment, we purposely did not treat with UVA and riboflavin so that the cells which are available in the rim can actually grow and come into the rim. But what we also did was to use the collagen which had been polymerized and treated with riboflavin and UVA, so that now the rim does not provide the cells because we have treated it with UVA and riboflavin. But we seeded the human corneal limbal epithelial cells on the surface, as I showed you in the workflow, and allowed them to stratify over 6 days. And this is the stratified epithelium that you can see in the NHNE staining. And you can also see the epithelium being formed by the CK12 staining. So we characterized it further. It is, of course, very much transparent and following all the collagen polymerization, cross-linking, and cellularization. And the thickness as determined by OCT was 477 microns. And you can see that the water content of the CLT was determined by thermogravimetric analysis, which showed that the hydration level was about 97%, which leaves the collagen to about 3%. Now, this fact and finding was very surprising to us, because the collagen that we used for polymerization was 0.15%, which is 1.5 mg per ml. but it had turned into a 3% collagen gel. Now, this is what I meant by saying that there's a phase separation of collagen that happens with the collagen-rich gel present within the central cavity and the collagen-poor solution, which is lying around and above and below the rim. So this kind of collagen polymerization was intriguing, and it is also, you would realize that this 3% collagen solution being generated out of what we used as 0.15% is probably only because of some kind of a morphogenetic influence of the rim, which is being provided to the collagen, which is polymerizing in the cavity region. And the normal collagen concentration, which is used by others in this field of work, is about 10 to 18% collagen. So this is really remarkable that using 0.15% collagen, you turn it into a 3% collagen, and yet you are able to have the same kind of properties as that of the native cornea. We further went ahead and determined its tensile strength by doing an amplitude sweep at 1 rad per second. And we determined the linear viscosity region, viscoelastic region of this using this amplitude sweep, and fixed the 0.1% strain to be able to do a frequency sweep, where we found that the G prime, which is the storage modulus, for all of these 3 samples that we generated of the CLT, were higher than the G double prime, which is the loss modulus. And this G prime being higher than the G double prime indicates that the CLT is displaying viscoelastic properties, which are enough for a surgeon to be handling them surgically. And these rheological studies were compared with that of a native human cornea, which also showed similar ranges of the storage modulus as well as the loss modulus. And then scanning electron microscopy showed that these fibrils were very much organized. They were tightly packed. And as I showed earlier, they were very well integrated with the rim. So basically, the corneoscleral rim here serves as a self-defining boundary that determines the diameter of the CLM that is generated. And we do not fully understand this polymerization, the differential polymerization of collagen, but there is some kind of a morphogenetic influence of the rim, because of which it is dictating everything that a natural cornea desires to be. That is its refractive index, transparency, curvature, thickness, and its ability to have a biocompatibility with the cells. And I would also like to point out that we used a particular rim at least 3 times, and we were able to regenerate, make the CLM and the CLT using the same rim. So even if the gap between the demand and supply is less for what is nowadays available for the donor corneas, we can reduce it even further because each rim can be used multiple times to generate the CLT. So this method is extremely simple. It is inexpensive. It takes about 2 weeks time from the time you get the rim to the final cellularized CLM, and you can use the same rim multiple times. So there are some very novel questions that this method poses. That is there something guiding the morphogenesis of such materials? Is there a morphogenetic field created by the tissue in the corneoscleral rim, which organizes the collagen into a cornea-like shape? To what extent is the ECM responsible for determining the shape of the cornea? Does the infiltration and population of a pre-organized ECM by cells lead to further reorganization of the collagen? And to what extent do stem cells provide information about structures, patterns, and morphogenesis and help in the formation of the CLT? I also believe that it is not that a particular collagen-like material has to be identical to the native cornea, because what actually is required is that the biocompatibility and the structural characteristics of the CLM, CLT, etc., or any bioengineered cornea must be the ones which are more important and should be akin to the normal cornea. This work has been published and also patented. And we have just recently, about 2 weeks back, got a grant from the ICMR to test this in actual keratoplasty in rabbits. Thank you so much. These are all the collaborators in this, and it is a teamwork with involving PGI, ICER Mohali, as well as INST Mohali.
Thank you, ma'am. I think phenomenal. Too good to be true. It's like the new cars, hybrid, EV with petrol. So you have the
Exactly, you're right, sir.
But
Absolutely, you're right.
I have a feeling that in our quest to develop normal human cornea, after this presentation, it looks we might be developing a cornea which is better than normal human cornea.
with no effort.
No, but
Very
mind-blowing,
interesting.
absolutely mind-blowing.
Very
mind
interesting.
blowing, absolutely unbelievable.
Mani, have you people tested the suturability of this material?
No. So all that will be now tested in the rabbits.
Animal model.
Okay,
Madam, can I ask you a
So
question?
we are actually thinking of doing both kinds of testing, that is using the fibrin glue for putting the cornea over which the contact bandage will be put, otherwise to suture it if it is possible. Yes, Dr. Velpandian.
Yes, how did you do the rheological studies? I mean, especially the classical bob and cup, it cannot be done. How did you modify to make it possible?
So Dr. Ashish Pal in
Uh-huh.
INST
Uh-huh.
has the parallel plate configuration for which this is
I
suitable.
understand. Now, that's not easy, It's not possible for everybody to do that one. It's very
So
specific.
first we tried it in somebody's lab in IMTech and we were not able to do it because
I
he
know
did not
that.
have that configuration.
Exactly. That's great.
Professor Velpandian, there is
Yes,
another
sir.
procedure
Mhm.
which we have tested with a professor in Bascom Palmer University.
Uh-huh.
Stretchability of the corneal.
Uh-huh.
There is a device that he had made,
Uh-huh.
and we were doing for some other research.
Okay.
To see the amount of the force required to stretch the cornea before it breaks.
That's the linear force we apply on the tissue to break it up,
Yeah.
right? So that's true. But this one is very interesting because when we try to do the bioadhesive property of the implants, we try to do in such a type of one is a flat plate type of one. It's not a classical cup and bob type of rheology, which is not that somebody who understands this process can only do it. Very nice, madam.
Right.
You took
Very
good
nice.
people around you. Very
Very
nice.
nice
I appreciate you for
idea.
that.
That was
Thank you.
fantastic, ma'am. Really. I understand it's very difficult
Amazing.
testing collagen like this. It's really beautiful.
Very good.
And I agree with your
Actually,
theory.
this was a serendipitous discovery
Yeah.
because we were trying to get fibroblasts out of the rim into the collagen. And the next morning, it was seen that actually the cornea has itself formed within the rim, and we just took it forward from there.
Very nice.
There have been a lot of approaches to this is mechanotransduction. Basically, it's the structure that is guiding the cells to
Yes.
work in a particular way. There are a lot of people trying to do this, but this is fantastic. Do you think that if the scleral rim is composing only of sclera, it would probably show this, or you need a little corneal periphery
No,
there?
I think that you need a little bit of that the amount that is actually left when we receive it from the eye
I
center.
think whether epithelial cells or endothelial cells or stromal cells, everything is coming out of the limbus. I mean, the area junction of the cornea and the sclera.
Yeah, and it is extremely reproducible. So we have done this in a large number of rims and it is very reproducible. The only thing that is not reproducible and not consistent is the ingress of cells from the rim itself. So that is not reproducible because that depends on the quality of the rim and how much time you received it after the donor cornea was used,
I
etc.
think those things need to be standardized.
Yes. So we
But
are
as
hoping
far
to
as
do
it
all
is
that
helping
now.
in this, it is good. I mean,
Yeah.
very
I
simple.
totally agree with you. Even with something which was not totally collagen, and we did this with corneal rim, not rims per se, but just pre-cut lenticle. So it had corneal tissue on three sides, and after 2 weeks, I was able to see ingress of native keratocytes even when it was stored in IMAC conditions. That was fantastic. So this definitely works, and we've seen this even with non-collagen materials. So that's the real hope.
Yeah.
Serendipity is the word of the day.
Yes.
Exactly. Absolutely.
So, Dr. Namrata, I remember AIOS in Bombay. You had mentioned to the reporters also about cornea. What has been your experience? You have also used artificial cornea.
So we've used stromal constructs. We are still not there where We've used complete constructs, complete corneal constructs. So as of now, what we have worked on and what we have used clinically is just the stromal construct. We are working to grow endothelial cells, but it is very difficult to grow endothelial cells on synthetic constructs. It's not easy. So in between, we also try to grow cells on the corneas which are not suitable for corneal transplantation. But then again, that is also a it's not a very easy proposition, although people have done it in other parts of the world as well.
Can I say something quickly?
Of course, sir.
The best part, which I think for the talk what Professor Mani gave, is like in situ regeneration of the cornea. Say, for example, you remove the scar with the femtosecond, the whatever the scar area is, and in that you just put this collagen and put a bandage contact lens. So maybe you put a fibrin glue or something, even though they have not done this experiment, but I would like your people, or
Yes.
you help us that we prove this is possible. Then what
Sure,
will
sir.
happen? It will become like a slat. You don't
Yes.
need to
Yeah.
work on anything. You just have a collagen solution as a drop and put on the drop after removing with the maybe with the excising, not necessarily with laser, but you can do with trephination and fill that crater with this material and allow it to develop.
Sure, sir. So I'll be in touch with you. Yes.
So it kind of gives tectonic, tectonic stability with transparency. I think that is the best part of this webinar, that everybody has got onto it together and we can have permutations and combinations to actually get the real cornea, or maybe even better than that. Today, I have come to believe that maybe we'll make corneas better than the natural corneas also.
Wonderful. I think that's the best thought we can leave today. But we
Yeah.
still have a main speaker. Dr. Mani, a lot of ideas that you will get back again in Manali. Do share more ideas. Have a wonderful vacation.
Thank you so much. Thank you for having me in this meeting.
You're welcome.
Thank you for
I mean, mind blowing. Everybody is taken away back. But now we have the star person who's coming next is Dr. Prasanna Ramesh, 3D printing from gamified and tactile ophthalmic. Now, let me give us brief introduction of Prasanna. He doesn't need actually. He's too got such a huge CV, but he's the research director in the glaucoma head at the Mahatma Institute, Trichy, India. And he has published multiple chapters, articles, editor-in-chief of. So I can keep going on, but I want him to talk about what's coming next.
Yes.
Now we spoke about cornea, but glaucoma, the next part, which is so very important. Welcome to the show, Prasanna.
Thank you.
And over to you.
Thank you, Himanshu sir. Thank you, Namrata ma'am, Himanshu sir, Virendra sir, and Tirumurthy sir for the opportunity. Hope I'm audible and my slides are visible. I'm going to start this with one of the models that I'm just holding in my hand. So this is so Dr. John made my job easier, but I'm just going to show what 3D printing can actually be more useful for is again going into the basic science of pedagogy. So this is a corneoscleral meshwork that we just printed, the uveal meshwork and the juxtacanalicular meshwork. I hope it's visible and maybe I'll show it at the end in the videos as well. So can we print concepts which helps neophytes understand and accelerate their learning was one of the problem statement that I started with. And we were seeing a lot of theoretical concepts when you go to a textbook like neuro-ophthalmology, you see a lot of structures that you don't get to dissect in your practice. Even in anatomy classes, a circle of Willis, a cavernous sinus, or even the eyeball models per se. So for bringing critical teaching, like Dr. John said, we need to have these models to really feel what we are really going to do. So these are some of the models that has been printed, the first of its kind, circle of Willis, cavernous sinus, the eyeball model as well. Because toys and puzzles are one that really improves intellectual knowledge. But in ophthalmology, even the eyeball, we don't get to dissect. These are all non-dissectable structures. Even during our anatomy classes, we don't get to do it. So can we really do something of this sorts using a Maya LT software? Where we used another slicing software to, printing the models has to be then got into a sliced layers, and then the output was done in a standard tessellation language. And finally, you can see this was how the models were made. These are all fine structures which we tend to imagine when we study the cavernous sinuses in total having the cerebral venous sinus, the sagittal sinus. So the Maya software using Cunningham's and Chaurasia, I sat and we have to read the anatomy and where they come and tend to orient themselves. So this was one of the prototype models which I am holding again in my hand, the circle of Willis. And then I had to go back, read the anatomy. Eyeball was one of the easier models to create. And once three-dimensional construction of these models were done in finite detail, that's when the challenge arose as to how we can have a prototype printing, especially for neophytes. So the printers were Fab Excel and FabX Plus printers were the one that I personally used. And polylactic acid, PLA, biodegradable materials were used. And you can see that the models were printed, a puzzle assembly kind of a concept for neophytes to start their journey into ophthalmology or neuro-ophthalmology, even glaucoma per se. You can see then you can paint it and get it sorted, and there comes your models where you can have a tactile learning feel by connecting the puzzles and where the anatomy really is, and then slowly evolve as you can see in the further slides which I'm going to show. So this is again the eyeball model where the sclera, the cornea, the fundus, even the angles that I just showed was printed in fine detail. Especially with the angle models, you can also demonstrate the different pore sizes that I'm showing in my hand. You're going to pour a liquid. You can see the juxtacanalicular meshwork is going to have a very small pore size where there is going to be maximum resistance to the aqueous humor outflow. All concepts can be demonstrated in a very practical manner. And one additive thing that was brought in our model per se is you can see the sclera, you can see the choroid inside, but the model that I'm holding in my hand is the plastic one for the retina. So in that you can bring layers of the true confocal fundus images. And it's like an automobile engineering where completely the eye can be, opened up and you can dismantle and mantle it. And these models can be used in training. And what really helped these models is the thermoplastic polyurethane for the retina, because you can continuously change a 2D color print paper and different model anatomies, pathologies, autofluorescence, infrared, like all varieties can be placed. And it really helps even in laser training and even for basic investigative procedures that a neophyte starts this thing with. And all the models which we created, especially the neuro-ophthalmic models, were tough to create, are actually available on the website. It's open access. And what really strikes the chord here is it's very economical. You can see that the circle of Willis or this cavernous sinus or the eyeball models, they're all very economical in INR. You can see it's as simple as that. The duration of printing takes quite a bit, that maximum a day or so, especially for the eyeball. Otherwise, it's 10 hours to 5 hours for the neuro-ophthalmic models. And these kind of puzzle making, and you can see now after this, I expanded the horizons along with my team, and we wanted to bring more into neuro-ophthalmology because I felt neuro and glaucoma go hands in hands, especially with the differentials. Can we bring a whole module of printing by adding more layers, the optic radiation, the nerves, the extraocular muscles? And this is the model that I personally created, the Maya LT software, where we brought more structures into play. And that was one of the innovations that is very, very yielding for students as well as for counseling. And another recent one where I started exploring is visual fields, because can we, animate visual field learning? Because again, that is another thing which I felt has a lot of scope to really decode. And because a cone, when you see on top, is just like a circle. Similar thing happens with visual fields, right? Because we tend to see a visual field and we tend to not see it in 3D because three-dimensionally it's a functional test. So can we have something, because I started with simple animation making of the grids, but that was not enough. Can we really push the horizons and bring something more? Because the reality is the differential light sensitivity, right? The macula is picking up very sensitive lights. So we wanted to print models, as you can see, a simple hill of vision, which is actually in my hand, and that really decodes different decibels threshold, what we really want to convey, because the hill of vision is finally an XY axis with the spatial extent of the visual fields, and the Z axis is sensitivity of light. So all these concepts, you can see that the concepts need a three-dimensional orientation to actually bring out understanding even to the patient or even for a neophyte, explaining sensitivity, thresholds, algorithms. So again, that's when if there is a visual field defect, you can actually really print it and you can really show what is a blind spot, what is an isopter contraction, because concepts like isopter contraction is something which is not understood that much. You can see again, I'm holding an isopter contraction in my hand, where again a similar software was used, again similar standard tessellation language was used with the polylactic acid. And it really makes a lot of difference in accelerating learning, especially for pedagogy, something I really focus on, because this gives you a complete hold on the subject and it accelerates the learning for the beginners. The 3D construction of it, how a normal ill of vision, how is a 10 degree, a 20 degree, what is an isopter, how is the blind spot, oriented, because these are regions that have not been explored. Again, isopter contraction was one that was always understood cognitively. Okay, the hill totally comes down, or the arcuate scotoma is one. Can we really print it? So the background, I'm not able to show this very clearly, but these all were printed and the videos are also showing the same. How is a scotoma, a relative scotoma, defined from an absolute scotoma? These kind of definitions. An absolute scotoma, it's like diving acutely from a point, you dive deep in. A relative is sloping and coming in. So concepts which are very important, short-term fluctuations, and much more, square root of loss variance, quadrantopia, the isopter contraction that I showed, that there is a generalized decrease in sensitivity, that the points are all generalizedly decreased, the hill just comes down, because in 2D, we don't get to see this. So it is something which really explores the way. And the last but not least is a metaverse that, which really, I call it the 4D printing or the holographic printing, these are the future, or these are the present, where we were able to crack an algorithm with real confocal images. You can see there are real confocal images where once the models are ready, be it this eyeball, be it the neuro-ophthalmology, you can actually go and trace the structures once an investigation is done. I can see sir holding a eye goggle in his hands as we speak. So this was cracked in 2022 by myself, and we did file the patent for it with the real confocal images, where not only you can see structures, you can also work on a level of EMR, which we are currently working on. Every investigation will be done, the patient's case sheet, or the 4D print, which I just fondly call as a pseudo print. You can trace the splinter hemorrhage. You can see on the right-hand side, once you wear the goggles, you can trace the splinter hemorrhages. You can trace the retinal nerve fiber layer defect, because patients come and give a case sheet print to us. What if the patient gives us a hologram that this is my case? I examined my eye and the doctor gave me a 4D case sheet or a 3D printed case sheet in a holographic manner. You trace the retinal nerve fiber layer defect. This is next level technology, and this is a museum that I have at my center in Trichy Mahatma Hospital, a neuro module, a glaucoma module, a retina module. There were times when we were making this, especially the neuro one, you can see it's a complex neuro module where we reduce the brain transparency so that every other three-dimensional structures, the nuclei, the radiation, the nerves are well seen. And this is another one which pushing boundaries, where you can actually push for surgical simulators. The first MIGS holographic surgical simulator, just like the Johnny Quest. For a millennials, Johnny Quest is something that you really aspire for. Can go and practice not once, but multiple times. This was my APAO LDP project, which I presented at APAO this year, which was well received, where you can go and practice the minute surgeries not once, but multiple times in real time modules, which is very cost effective. So that's the catch here. And you go and do your implants, as Dr. John told, which was published in the 10 questions, 10 pros at the AOS Times. And I would also like to acknowledge my team. I started my own startup. It's an MSME registered Mahatma Center of Moving Images. It's a proper startup. And this uh, set of innovations, which actually put me this year at the Sightline ASCRS, recently concluded in LA, where I was able to win a grant of 5,000 US dollars for this particular innovation of mine, where one of the very few Indians to win this competition on the global podium. And not only that, it's more of the grant that you get, 5,000 US dollar grant. to invest in research, invest in R&D more. And we are coming out with more and more applications. 3D printing, virtual 3D printing or hollow 3D printing is another extension which really pushes your boundary, where it's a very beautiful time where you can subtract structures. You can virtually dissect. So this is a app A to Z made by myself where you subtract structures that you don't want to. You dissect with your hands virtually, as you can see on the left-hand side. And even pediatric ophthalmology is something that I've started exploring into the brain structures of the sulci and gyri, and 3D smartphone simulator for ophthalmoscopy for MLOPs. On day one, you can have a smartphone, go into the eye, come out just like a direct ophthalmoscopy with a spatial 3D orientation. With all the models ready now, model creation was very tough because I had to go back to anatomy and read it. But now with the models being created, I think slowly we are pushing boundaries and moving into investigation, surgical, EMR, and whatnot. And this is a project I'm working with Dr. Tanush sir for the aqueous outflow channels. Very recently started one. I'm grateful to sir for this wonderful opportunity, and many, many more. And all these are published, well documented, well evaluated, peer reviewed in literature. And these are some of my own references, and many institutes like Arvind. Recently, this was my three-dimensional circle of Willis model that you can see in my hand, which is completely 3D. But the prototype model was not this 3D. So today, to have a structure of this fine structure in a three-dimensional hinging is not that easy. It took me 4 years to get the circle of Willis exactly the way what it is. And many institutes have started buying it for their undergraduates and their postgraduates. Again, I do have some financial disclosures because I have started my own startup, the Mahatma Center of Moving Images. I want to disclose it. And I'm coming from, again, you can catch me in Instagram or on WhatsApp. I would be happy to share more. Thank you once again, Namrata ma'am, for this wonderful opportunity, for giving me this chance to be here among all innovators whom I've always looked up and learned a lot. Thank you.
Wonderful. Absolutely mind-blowing, Prasanna.
Excellent. I appreciate him for that.
I was just seeing the Apple one. Have you seen the cardiology, the heart on the Apple virtual?
Yes, sir.
If you could make that for the eye, you made a circle of Willis, but if you can do that for this, I think it is amazing. It's amazing with the pinch technology that you are doing. It's a brilliant, brilliant innovation.
Thank you, sir.
Dr. Sangwan, would you like to comment on what Dr. Prasanna has to say?
Yeah, absolutely fantastic. I think diversity of presentations we had today evening is fantastic. It's given us a very rich experience and many ideas that I will pursue with many of them one on one. So it is really very nice, and thank you each one of you.
Dr. Pandian, would you like to mention?
Yes, Prasanna, yes, I appreciate you for this. And amazing. It gives the finest details. This is something which is really amazing, and it is a need of the hour. And it will be highly helpful for everybody to understand. Often we fail to give the complete imagination of the structure. I appreciate you. Kudos. Great.
Just blurred my background a bit. So this is the visual field structures, because isopters are something every time we expect the students or the counseling, we expect them to mug up, certain things like a simple isopter contraction. So this is how an isopter contraction looks in 3D, but in textbook we get this view. And every time in exams, the students just draw two hills and they don't really give a thought of what is a real isopter contraction. It is just the decibels that is coming down in sensitivity, and it just the whole hill comes down. So I think, sir, as Dr. John also showed, we really want to accelerate the learning. And if I have time, this is the real three-dimensional circle of Willis model. This was my prototype. So when I did the prototype, you can see that the Z-axis is not in play. It's just a XY axis where it was more of a horizontal plane. So to then expand it and bring it into a real 3D. So this is the real circle of Willis because we don't tend to dissect it. So even in books, if I want to see it from a side angle like this, I don't get to see it. I get to visualize and imagine it. But now I can show a top angle view of how the real Willis will really look and how you really see it from every anterior, posterior, lateral. And I think that's the whole idea, sir. And that's when I think from Virender Sangwan sir's HoloLens, when sir was working on, I was following it very closely, sir. That was one of my inspirations to move into mixed reality and extended reality, to crack the code for confocal images wanted to bring confocal images into play and make it as real as possible, sir. I think we are just inspired from works like you, and we are following your footsteps, sir. Thank you.
Very nice efforts.
I think amazing conversation we have had. This would have not been possible without the support from Navneet and Ashok. Please come in front, Ashok. I genuinely.
Thank you, sir. Thanks.
Thanks very much for organizing this and getting everybody together on the same platform. I think each one is more wiser and happier after the whole thing. Till now in my life, I had only seen Google QR codes to pay money. First time I saw the QR code from John that.
True.
Each one had phenomenal things to contribute, the 3D dimensional
Very
things.
nice.
I guess everybody has phenomenal. And any passing comment, it couldn't have got better than this. And we must promise to get you guys back again. Yes, John, you were saying
What is
something.
that, John, you are showing?
So I'm just showing the 3D printed glaucoma drainage device.
Okay.
Beautiful.
So even the extraocular muscles that we are working on now, if we are able to align it in such a way that we can actually mimic their responses, that is something that we are working in the pipeline. All the extraocular muscles, and if you are able to hinge it in a certain way, the whole teaching itself will be easy, because the whole concept of teaching will get accelerated. That is one which actually John and myself, we worked very closely for the last decade or so, from our days in Pondicherry where we shared together.
So maybe think of some micromotors or something attached to the muscles, and then connect with the stimulus. So that will give a real time the experience of feeling how the muscles are behaving.
Sure.
So Prasanna, I was just remembering my early days of anatomy, anterolateral, inferomedial, never understood, and all that for first 6 months of Grey's Anatomy. So the 3D model makes life so much more easier. I think brilliant session, phenomenal. Dr. Vineet, thank you so much. Dr. Namrata, if you're still there, thank you so much for being there always and giving us your input at every given point of time. Thanks everybody for participating wholeheartedly, and thank you, Dr. Sangwan sir and Dr. Pandian, for your valuable time. Thanks very much, everybody.
Thanks a lot.
With a great thing signing off today.
Great.
Sorry,
Good night. Good night. Thank you.
Group photo.
Group photo.
Yes, group photo. I'll take a group photo and I'll send it to everyone.
And
Dr.
somebody will
Namrata,
give
if you can come in front. Ashok, come on, you come on. Don't hide behind. Navneet, you guys are. Come on, Ashok and Navneet, come in front. Okay.
Ashok is not in formal.
I've got a group photo. I will send it. Yes.
He's not in formal.
Light on top. Navneet, switch off the light on top of you. It's counterproductive. Okay. Yeah. Okay. Better. All right. So I will share this photograph with everybody.
Thank you very much. Thank you. Good night.
Good night.
Thanks to everyone. Thank you.
Good night. Thank you, sir. Thank you.
Thank you, Himanshu sir.
Vineet sir, good night, sir.
Hi.
Nice catching up again, sir. How are you doing, sir?
I'm good.
Good night, sir.
Thank you, sir. Thanks to all of you, sir.
Thank you.
Thank you. Shall we exit? Ashok sir?